Well, good morning, students. We are again meeting virtually this week. I hope you all get an opportunity, clearly if you're watching this video, that you've been able to catch it. I will have a supplementary video that you will find also linked here to help us talk through what we're going to cover today. We're going to pick up the same place we left off in class last week when we met in person, covering parallel and series circuits. However, for today, we are going to try to cover specifically the nature of resistance over these two kinds of circuits. On a series circuit, what we will find is that as you add resistors to a series circuit and continue to add them in there, the overall resistance of the entire circuit is going to go up. And that's going to be found through an equation that just simply adds them. But in a parallel circuit, the overall resistance overall from start and finish will go down. And that's because each electron is going to have the opportunity to travel by itself down each one of the branches, thereby lowering the resistance. And so when we want to find the total resistance over a parallel circuit, we need to add them as the reciprocal. So as a fraction, 1 over the figure that we have for resistance in a parallel circuit. And what we'll find is that it actually decreases the overall resistance for the entire circuit when we're dealing with a parallel circuit. The two other things that we even covered in class, and just as a reminder, is that a series circuit requires one path for the electron to flow, so that if any one bulb were to burn out, the whole circuit would go down. But in a parallel circuit, because each resistor has its own branch that it can go down, you can have a bulb that will burn out and the rest will continue to shine. And that we see applicationally in our homes, the way that our lights are wired through our house. And you'll find the same information repeated through the supplementary video that I'm going to include. I am going to draw it out real briefly here, as I would if we had the whiteboard in class, although I won't have as many questions for how we deal with the math, but I want you to see if you can pay attention as we go through it together. Okay, for today we're going to continue looking at parallel and series circuits, and this time paying special attention to the nature of resistance over the whole circuit, distinguished between parallel and series. So to begin with, let's start with the easy one. We're going to start with a series circuit. So here we're going to make our power source. Let's make the picture here of our switch, and then we will add in our 3 resistant light bulbs and then close the circuit again. So this is a series circuit because there is only one path for the electron to go. So the current flows from positive to negative. Electrons are flowing from negative to positive. And if at any point we were to break the circuit, we would find that there'd be a breach so that the electron current or electricity could not flow at all, and therefore if any one light were to go off, all of the lights themselves were to go off. So let's add some resistance values to each of these bulbs. This one we'll say is 3 ohms, this one will be 5 ohms, and this one will be, I'm just going to draw over my arrow there, 4 ohms. And for our battery source, we'll call it a 12-volt battery. Now, in order to determine the resistance over the entire series circuit, the way we find our total is by adding up the resistance from each one of the bulbs. So for each one of the resistors, 1, 2, and 3, we find the total simply by adding 1 plus 2 plus, R3. So resistance of 1, 2, and 3. So the first one was 3 ohms plus the second one, which was 5 ohms, plus the third one, which was 4 ohms. And for this, we will determine that the total value is 12 ohms over the course of the entire series circuit. So this is real straightforward, very simply how we find resistance over a circuit that is in parallel. Now, you'll remember too, as we taught Ohm's law, the trick of drawing our little triangle, V over IR, that if we want to solve for the current, if we want to find how many amps are being drawn through this circuit, we can easily just cover that one up, and we see that it is voltage divided by the total resistance. And in this case, if we put those values in, our voltage is 12 volts divided by 12 ohms, and that gives us 1 amp for the whole circuit. All right, now let's look at one in parallel and see if we can determine the nature of the resistance of a parallel circuit. So we'll draw our power source in, add our first branch, and then add in our second branch, and finally our third branch right here. We'll call this one R1, R2, and R3. When we're looking at a parallel circuit, one of the things to keep in mind is that each loop where the electron can travel can be recognized as its own circuit. That here is one, that's a second one, and then here is a third path that electron can travel through. So unlike in a series where your voltage is going to drop as you come to each sequential resistor or lamp, here you get the full voltage amount that travels over each resistor. So in a 12-volt circuit, you will have a total of 12 volts traveling over this one, 12 over this one, and 12 volts traveling over this one. Now, we'll make our resistance values the same as we did up here, so 3, 5, and 4. But this time, what we're going to find is that the total resistance over the whole circuit isn't found by just adding up the resistance values, but because each of these can be thought of as their own loop, as their own circuit, you actually will see that the total resistance will drop. It will actually go down as you add more resistors to the overall parallel circuit. And this is described with the equation looking at the reciprocal values of the ones we have up here. So the total is going to be 1 over the total resistance, which will be equal to 1 over R1 plus 1 over R2 plus 1 over R3. So if we were to add in these figures, we will find R1 is 1 over 3 plus 1 over 5 plus 1 over 4. As I am looking at this figure right here, it's going to do a little bit easier for mathematics if we turn this 5 into a 6. So let's just change this for the sake of adding fractions, because if you can remember how to add fractions, we have to get a common denominator throughout each of these. So the lowest common denominator between 3 and 6 and 4 is 12. And when we adjust these according to 12, 1/3 in twelfths is equal to 4 twelfths, 1/6 is equal to 2 twelfths, and 1/4 is equal to 3 twelfths. Adding all these together, we get a total of 9 twelfths. Simplifying that, our total is 3 over 4, or 0.75 ohms overall. And as we would find, if we continue to add more resistance to this circuit, we will find that the overall value will continue to drop. So that is the unique differences between a series and a parallel circuit. Again, as a reminder, a series circuit is where you will add up all of the resistance to find the overall resistance for the circuit. And a parallel circuit, you will add up the reciprocal. So a fraction showing 1 over the value you have for the resistance on each bulb, so that the overall continues to get smaller with the more bulbs or resistors that you add to the overall circuit. I want to encourage you again, I'll put a link on here for the University of Colorado, the simulator, and my challenge for you for homework is to see if you can replicate these same values that I drew out there on the paper in this video by making your own circuits and see if you can find the same results by testing the voltage and the amperage and using Ohm's law with that. So that link will be posted there below. Have a little fun with it. Should only take you a couple of minutes. You can play around with it even more beyond that. And then we are going to be virtual again next week, but we'll see you in person not too long after that. So stay safe and have fun. Take care. Bye.